And we had talked about that there were a bunch of different methods that we could use to solve a system of equations. We've been talking about using graphing to do that. So let's look at a quick example here. We had said if we wanted to solve this by graphing, the first thing we'd want to do is to get these equations into slope-intercept form. So the first equation, I can just subtract 2x from both sides. And in the second equation, I'll subtract x from both sides, and then also divide by -1. And then to graph each of these, I'm going to make an XY table. We had talked about when making these XY tables, it's often going to be probably better if we pick our x's so that they're kind of far apart, just from a practical, actually having to graph these things standpoint. So I'm going to pick, say, 0. When I plug 0 in for x, I get 5. And then maybe, I don't know, let's just say 5. When I plug 5 in, I get -5. I do the same thing over here. Let's say I plug 0 in. Gives me -10. And then maybe I'll pick 10 this time. That's going to give me 0. And now I'm going to graph both of these two lines on the same XY axis. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. So I have 0, 5, and then 5, -5. So that first line's going to look like that. And I have 0, -10, and then 10, 0. One's going to look like that. So it appears that this is my intersection. So we would suspect the point 5, -5 is our solution. i.e. when x equals 5 and y equals -5. Right? I think we've gotten through one example of this situation, right? So let's ask this question. let's ask ourselves, what could these solutions to a graphing problem look like? Well, we could have one solution that is a single point of intersection. Right, that's what we just saw above. But what else could happen if we have two lines? You have 2 points of intersection? Okay. Do we have a name for that? Yeah, so that would make 0 solutions. And then there's one other possibility. You have one solution, you can't have no solutions. What would the other possibility be? Well, remember these lines have to be straight. You could have infinitely many solutions. What would that look like? Yeah. So the lines are not distinct. I.e. they're both the same line. So like, if this is one line, then like, that's the other line. So at every point on the line, they intersect. You guys need to stand up and turn off the lights if it's hard to see what we're doing. Again, first hour it gets rather dark, so usually don't have to turn the lights out because it's so dark outside. But I'm good with whatever you guys want to do. Just saying. All right. So we've done this solving by graphing. Now, a couple of examples. Let's make a pros and cons list of kind of the benefits or drawbacks to this as a method. We've seen a little bit of how this works, right? So, pros. Well, it's visual, right? It's easy to kind of see what the solution or what situation you'd be in, whether you have like an intersection or not, or the same line. It's pretty easy to do, right? We all remembered when we talked about Algebra 1 skills, we all remembered graphing lines as an Algebra 1 skill we spent a good amount of time doing. It should be a skill that we're pretty comfortable with. Well, let's think about some cons. Well, it's a little time and space consuming, right? To draw a graph for 2 lines, it takes a little bit of time and effort to kind of do that, especially considering that neatness counts here, right? If you're not drawing a very neat graph, it makes it really difficult to get an accurate answer out of here. Let's see, what else is a problem? Yeah. So, like, this affects your accuracy. There's 2 more major drawbacks that I can think of. What would happen if my equations had 3 variables in it? Now you're trying to graph in 3 dimensions, which is still doable. It's not very easy to do on a sheet of paper, though. But what if I had 4 variables? Or 5, or 6, or 7? Not very practical anymore, right? So not a very easy method when we start getting into more than 2 variables. There's one other major drawback that has a little bit to do kind of with accuracy and neatness. So right now in the examples that we've looked at for graphing, our solutions were all integer solutions. Do they have to be integer solutions, though? No. How likely would it be to be able to tell the difference between a solution like 5, -5, and 4.99 and -4.99? Not really easy to do that, right? You'd need to be tremendously accurate and have like a massive sheet of graph paper and be really kind of careful about graphing that. I mean, you could get it, but probably not realistically and not very quickly. Like that would take a lot of kind of time and effort and space to get something like that. So if you're just looking at a point, like the point 4.99, -4.99, looks a lot like the point 5, -5, and it's unlikely you would be able to tell the difference. Yes? Realistic to get fractional or decimal answers or solutions. So if we compare these 2 lists, where do you think we land on for this method? Not that great. in fact, is a method that realistically I would never choose to use. It's a nice starting point because it's visually very intuitive to kind of see what's going on. But from a realistic standpoint, if we're actually going to try to solve a system, this is not the method I would use. It has a lot of drawbacks to it. Now we can mitigate some of them by using our calculator, and we'll talk about how to do that, probably not today, but maybe next time. So next time, if you guys please remember to have your graphing calculator, and we'll talk about how we can use graphing on our graphing calculator to get answers. But it still doesn't help us for this part. So even using the calculator mitigates some of the drawbacks, but not all of them. We're still going to have a little bit of an issue there. So we're going to move on to some algebraic methods. That don't require the use of like a graph or geometry to be able to do that, or to be able to solve them. The first one we're going to talk about is called substitution. And I'm not going to describe here in detail the steps for substitution because they kind of are a little bit based on decisions that you'll make. So we'll just kind of talk through an example or two here slowly and carefully, and about what our goal is going to be during this solving process by substitution, to make our to try to make this as easy as possible. Okay. So right now I have two equations with two variables. Everybody can see that? What I would like to do is be able to change this into a situation where I have one equation with one variable, because that's something we can solve very easily. Everybody okay with that idea? One way to do that is using the process called substitution. So what substitution is going to do is it's basically going to allow me to solve for one variable in terms of the others, and then plug that answer into one of the other equations. Thus, I kind of eliminate that variable from it. So the first choice it's going to be that I'm going to have to make is I need to choose an equation and then choose a variable that I want to isolate from that equation. So for the sake of us talking about them, let's call these equations 1 and 2. Now, this is a place where you can make your life much easier or much harder depending on the choices that you make. The problem is always going to be doable regardless of the choice you make, but you can certainly save yourself some time and effort if you choose wisely here. So we have two equations, each with two variables. We have four possible choices of the variable we want to isolate. There's one choice in this situation that would be a bad one. Which variable would be the one that I wouldn't want to try to isolate? The 2x. Absolutely correct. Why would that be a bad idea? In isolating the 2x, I'm going to create a decimal or fractions. If I can avoid having to do that, that makes this process a little bit neater and a little bit easier. So, me personally, I'm going to always try to choose the variable I want to isolate by trying to minimize the amount of decimals or fractions I create. So, for the sake of argument, let's say that we're going to get this, or isolate this y. So to do that, all I need to do is subtract 2x from both sides. I'm going to call that equation 3, just so we have, when we refer back to it, we have a name for it. Everybody's okay with that? Maybe this would be better to name these letters. Maybe I'll call this A, B, and C here. That might be a little less confusing in the long run if they're labeled with letters as opposed to numbers. What do you guys think? Maybe? Just seems like we have enough numbers rattling around in here. All right. So, what this is telling me is I know now what y is equal to. Y is equal to negative 2x plus 5. So what I can do is I can substitute negative 2x plus 5 into the other equation in place of y. Now, important thing to note here, I cannot ever substitute back into the equation that I started with. That's a bad idea. Everything is just going to cancel out if you do that. Have to make sure you're substituting into an unused equation. Everybody's okay with that idea? Okay. All right. So when I do that substitution, I have x minus, and then in place of y, I'm going to write instead negative 2x plus 5, and then I have equals 10. I'm going to call that equation D. Notice now when you look at equation D, how many different kinds of variables do I have in here? Just one. I have just x's. This we can solve for. So I'll just distribute my negative. I'll combine x and 2x to give me 3x. I'll add 5 to both sides. And then divide both sides by 3. But this is only halfway. Right? How many answers am I really looking for? I'm looking for an answer for x and an answer for y. I have only my answer for x right now. So I still need to do a little bit more. How am I going to get my answer for y? Annalise? Yeah, so there's actually 3 choices of where I could plug in x equals 5. I could plug it into equation A, into equation B, or into equation C. I cannot, though, plug it back into equation D. Why not? There's no y's in it. Right? How am I going to solve for y from an equation where there's no y in it? Yes? Yes. So it does not matter which one you plug into. So let's think about here which one of them would be the easiest one to plug into. A, B, or C? C. Why would C be the easiest to plug x into? Because the y is already by itself, right? You don't have any solving to do. Oh, okay. So we're just going to plug that into C. So I get then y is negative 5. So we can say our solution then is the ordered pair 5, negative 5. So when we write our solutions for these systems, we are going to write them as tuples, like an ordered pair. The order that we write our answers is always alphabetical. So x comes before y, so our answer for x should come before our answer for y. If we have, say, our variables are a, b, and c, our answer for a would go first, our answer for b would go second, our answer for c would go third. Doesn't matter how many variables we have that we've solved for, we always write them as a tuple. That's what we call that, like an ordered pair is a kind of tuple. You could also have a triple or a 4-tuple or a 5-tuple or whatever. But we always write the answers in alphabetical order like that. Is everybody okay with that idea? All right. So this is a situation where we had one solution, right? What would it look like if we were solving a system by elimination that had no solution or infinitely many solutions? That's an important question, right? We know what those would look like graphically, but we don't know right now what those would look like, what would happen algebraically. So let's look at an example where that sort of thing happens. So the first thing we need to do is we need to decide which equation and which variable from that equation do we want to isolate. What would be the best choice here, Helena? Equation A and which variable? Y. So easy to see that solving for y is going to give us no fractions or decimals. That's a good safe pick there. That's probably what I would have chosen. So to get the y by itself, we'd subtract 2x from both sides and then divide by a negative 1. To give us y equals 2x minus 3, and we'll call that equation C. Now I'm going to use equation C and substitute in the value for y into equation B. Notice the only part of equation B that's going to be replaced is the y part. The coefficient, that is the 2, is going to stay there. Everybody okay so far? Okay. So we'll just distribute that 2 through. And negative 4x plus 4x gives me 0. And I'm left with negative 6 equals negative 6. Is that true? Does negative 6 equal negative 6? Yeah. So what this tells me then is that this is the infinitely many solution situation. but I want to do more than just write infinitely many solutions. I'd also like a description of what those infinitely many solutions look like, or how to find them. To do that, I'm going to use equation C. So what do the y's look like in the solutions? Well, they have to look like 2x minus 3. So my solution set is going to be things of the form x comma 2x minus 3. So for example, what that says is I can pick any value for x, and if I find my y by doing 2x minus 3, that's going to be a point that solves the system, or is going to be a solution to that system. So for example, 1, negative 1 would be a solution. 2, 1 would be a solution. 3, 3 would be a solution. 4, 2 would be 4, 5 would be a solution. Is everybody okay with how I'm generating these values? Okay. Are we okay with where I came up with x comma 2x minus 3? So again, using that equation C, whatever my independent variable is, and then the dependent variable gets the expression. So if I had written this in terms of, if I had say solve for x in the beginning instead of solving for y, I'd have expression of y, comma, just the letter y as my answer. And that's okay too. Again, you could have different answers here. They should generate all the same points, but you could have different answers. So this piece right here is what the infinitely many solution is going to look like. So you should end up with like a true statement like that. 4 equals 4, 0 equals 0, 1 equals 1, negative 6 equals negative 6. Something like that that's always true. What was this that you did? 2x minus y. So let's say we have the system 2x minus y equals 3, and then negative 4x plus 2y equals negative 5. Notice this is almost the same system as the previous one, right? What's the only difference? It's almost the same system as the previous one. The only difference is that this is minus 5 instead of minus 6, right? That was the only thing that changed. Okay. But apparently that's going to make a big difference here. So, just like before, let's isolate the y here. And just like before, we'll substitute that in for the y in the second equation. So doing the same thing that we did in the previous problem. Since it's almost the same thing, there's no need to do anything differently. And then I have negative 4x plus 4x. Those cancel out. And I'm left with negative 6 equals negative 5. Is that a true statement? No, that's false. That's always false, right? So what does that tell me? No solution. And you don't have to do anything more than state no solution there. Andrew. Right, you can't substitute in back from whatever you made, right? That is always going to give you nonsense, because if you solve one equation with itself, like that's always going to happen. You have to plug it into the other one that you haven't used yet. Okay. So everybody, so far so good in terms of what these infinitely many solution, no solution situations are going to look like algebraically when we solve them? Grace? Sure. Elena? We're solving? Yeah, we're just solving. So, there is a little bit more going on here, or an observation that could possibly make this process a little bit easier. So let's go back here to this first example. If you compare equation A and equation B, do you notice anything about these two equations? Andrew? Yeah. Everybody can see that? Or you could have, if you prefer, you could write it as equation B is -2 times equation A. You could think about it that way also, if that feels better to you. If you have that situation where one equation is a whole, like a multiple of the other equation, that's always going to give you infinitely many solutions. So on a homework or a test or a quiz or whatever, you could make this observation and go straight to the infinitely many solution situation. What that doesn't help you with, though, is being able to describe the nature of the solution. But at least it tells you right away what's going on. Does everybody see that observation? Let's look at the same thing here. What do we notice going on when we compare equation A and equation B in this example? Notice that the left-hand side of equation B is equal to -2 times the left-hand side of equation A, but the right-hand side of equation B is not equal to -2 times the right-hand side of equation A. Did you guys see that? Where those sides are multiples of each other, but that side is not. We can see that? Yes? Yes? If that's the situation, you're always going to have no solution. So instead of doing the solving process, you could make that observation and say no solution and be done with it. That's okay. If you are doing your homework or a test or a quiz, you can always make that observation and skip having to do the solving. And as my suggestion, really before I start the solving process, I'm going to check and see real quick by just taking a quick look at what my equations are, if it's going to be a no solution or infinitely many solution situation. Because it just takes but a second to look with my eyes to see if either of those two things is going on. It's helpful to know that right away. You know what I mean? Is it necessary you make that observation straight from the get-go? No. You'll still catch it along the way during the solving process, but it could allow you to save yourself a little bit of work. Everybody's okay with that? Okay. So the next solving technique is called elimination. This is another algebraic technique. It's similar to substitution, but it's probably one that, while some of us I expect have done a little bit of solving with substitution, I think maybe even that happens once or twice occasionally in geometry course, where you had to bust out substitution to solve, you know, you have like a bunch of angles or whatever drawn together and you have to solve for x, and like one of them you have to do like a little substitution in order to do the solving. It's probably much less common case for you guys who've done any eliminations before. Now, while elimination might feel less familiar right now, I think it's the better of the two methods. The reason I think it's the better of the two methods is I think it scales to larger problems better than substitution does. If the problems get bigger, they involve more equations and more variables, I think substitution gets more difficult, whereas I don't think elimination gets more difficult. Everybody okay with that idea? Okay. All right, so let's take this same boring old equation that we've worked with a bunch of times now. Oops, and that should be, what was that equal? It was 5. No, it was 10. What was it? I forget what I had written before. Oh yeah, it was plus. And then it was, okay. All right. So for elimination, what we're going to be doing is we're going to be adding multiples of the two equations together so that when we add them together, one of the variables cancels out or eliminates. Now, this is a very easy situation because if I look at this right away, if I just add these two equations without doing anything else, what's going to happen? The y's would cancel out, right? Everybody agree with that? If I just add equation A and equation B, I get 3x I get 0. I'm not going to bother writing anything since it's 0. Equals 15. That's pretty nice right there, right? I can then just divide both sides by 3 and get x is equal to 5. Right? How rad is that? If I substitute 5 back into either equation A or equation B, I can then solve for y, correct? Does it matter which one I plug it into? No. Just for the sake of argument, I'm going to plug it into equation A. So my solution is 5, negative 5. Let's do another. Yeah? Maybe one that's not quite as trivial. Okay. So let's say we have 2x minus 3y equals 6, and then 5x minus 6y equals 12. My goal is here to add a multiple of the two equations together so that we eliminate one variable or the other. So again, much like the substitution problems, you can make your life harder or easier depending on your choice that you're making here. Although, regardless of the choice you make, it will still work, but sometimes you can make your life harder than it needs to be. So, here, should I try to eliminate the x's first or the y's first? I would try to eliminate the y's, because all I need to do that is multiply equation A by negative 2 and then add it to equation B. Because when I do that, I'd have positive 6 plus negative 6, which is going to give me 0. Or positive 6y plus negative 6y, which would give me 0. Everybody okay with that? Just for the sake of argument, what if we wanted to say we picked to eliminate the x's? How would I do that? Well, I could do negative 5 times equation A plus 2 times equation B. If I do that, I'd have negative 10x plus 10x, which would give me 0. Either way of doing this would be fine. Everybody's okay so far, so good? All right. So I'm going to write out this. So when I multiply equation A by negative 2, I get this. And then I don't have to do anything to equation B, so I'm just going to copy that back down. Yes. I picked it so that when I add the y's together, they're going to cancel out. Does that make sense? So you have to pick the coefficient that you want. In the first problem, we didn't need a coefficient because the y's were already opposite signed, right, with the same coefficient. Here, the coefficients are different, so I have to make them the same somehow. I'm sorry, what are you asking?
Like, if we get 2 and 5, and then 2 and 5 for the y's, so like, you can't like multiply anything with 5.
You could multiply both of them together, like we did in this, where we eliminated the x's. You could multiply each of them by something different to make them the same. Is that okay? Okay. So when I do that, I get x equals 0. And say when I plug that back into equation A, I get 2 times 0 minus 3y equals negative 6, or positive 6, excuse me. So y would be negative 2. Or, if I had tried to do this the other way, and when I plug that into A, you'll see that I get the same solution. So it didn't really matter there, right? We got the same solution either way we tried to do it, whether you tried to eliminate the x's first or the y's first. You got the same answer. So once you get good at elimination, I think this is the easier method. It typically results in less things to write down. And as the problems get more complicated, when we add a third variable and a third equation, I think elimination becomes tremendously the shorter or quicker technique. So it is something that you're like, well, I understand substitution. Why do I need to bother with elimination? I promise you elimination is less time consuming the bigger these things get. Elena. You can use both. Yeah, you can use either one. They both work all the time. For me personally, it would depend for these two variable problems, it would depend on the setup. So in a problem where x and y are both on the same side, I'm probably going to use elimination. If I have an equation where I already have an x or a y isolated for me, I'll probably do substitution. But it doesn't really matter. But what you bring up is a good point. For us to use elimination, we really want the problem to start where I have x's and y's on the same side lined up and the constant on the other side lined up. If I don't have that, I would need to do some rearranging before I started my elimination. More often than not, you're going to be in a situation where one or the other is going to be the obvious one to use. Questions about what we've done here so far today? What is a infinitely many solution or no solution situation going to look like when we're doing elimination? The same thing's going to happen, right? When you add the two equations together, one side is going to cancel out, and you're probably going to be left with 0 equals 0, or only one side is going to cancel out, and you're going to be left with like 0 equals 2 or something. But you draw the same conclusion. Okay. So for